Scene script. Have you ever wondered why your room gets messy over time but never cleans itself? This is not just about your cleaning habits but a universal principle called entropy. Let's dive into the fascinating world of entropy, a principle that permeates every aspect of our lives, often without us even realizing it. Consider this, you've just tidied your room, yet given a few days, you'll find it's back to its usual chaotic state. No matter how hard you try, it seems impossible to maintain that initial order. This isn't due to any lack of effort on your part, but rather a fundamental law of nature. That's entropy at work. Or perhaps you've sprayed your favorite perfume in one corner of the room, only to find its scent wafting throughout the space a few moments later. This isn't magic, but entropy. The molecules of perfume spread out, moving from an area of high concentration to one of low concentration, in a spontaneous quest for maximum disorder. Now think about the last time you watched an ice cube melt. The structured arrangement of water molecules in the ice, trapped in a solid state, eventually gives way to a more random, disordered, liquid state. Again, this is entropy in action, driving the transition from order to disorder. Entropy, in essence, is the measure of disorder or randomness in a system. It's a concept from the realm of thermodynamics, the science of heat and energy transfer. But as you can see, it's not limited to high-level physics. It's an everyday phenomenon, governing the behavior of particles in physical systems, from your messy room to the diffusion of perfume to the melting of an ice cube. These seemingly mundane examples encapsulate the essence of entropy, a principle that dictates the natural tendency towards disorder and randomness. It's a fundamental law of nature, constantly influencing the world around us, even in ways we might not immediately recognize. Interesting, isn't it? How these common occurrences are actually examples of a fundamental physics concept. So, what exactly is entropy? In simple terms, it's the measure of disorder or randomness in a system. Now, let's break it down a bit further to make it easier to understand. Imagine you have a box of building blocks. When you first open the box, all the blocks are neatly arranged. But as you start to play, the blocks get scattered around. The scattered blocks represent a state of higher entropy, or more disorder. The neat arrangement in the box is a state of lower entropy, or less disorder. Now let's bring this concept into the world of physics. In a physical system, particles are like our building blocks. They can be arranged in many different ways. Each unique arrangement is called a configuration. The more ways the particles can be arranged, the higher the entropy of the system. Think of it like a game of musical chairs. If we have 3 people playing and 3 chairs, there's only one way everyone can sit down. That's low entropy. But if we add more chairs into the mix, suddenly there are a lot more ways the players can arrange themselves. That's high entropy. Entropy is also linked to the concept of probability. The more ways particles can arrange themselves, the more likely it is that the system will be in a state of higher entropy. That's because there are simply more options for disorder than there are for order. Let's go back to our box of blocks. It's far more likely that the blocks will end up scattered rather than neatly stacked. That's not because the blocks prefer to be in a state of disorder, but because there are simply more ways for them to be scattered than arranged neatly. And that, my friends, brings us to a fun, everyday example of entropy in action. Ever wonder why your room doesn't clean itself? Well, it's not just because of your lack of motivation. It's because there are far more ways for your things to be scattered around than neatly organized. This is why your room doesn't clean itself. It's all about the higher probability of disorder. Entropy isn't just about messy rooms. It's a crucial concept in thermodynamics. Now let's dive into the way entropy plays its part in the field of thermodynamics. Thermodynamics is the branch of physics that deals with the relationships between heat and other forms of energy. And entropy, my friends, is a star player in this field. It might seem like a complex term, but at its core, entropy is a measure of disorder or randomness in a system. The higher the entropy, the higher the level of disorder. Now you might be wondering, how does this tie into thermodynamics? Well, the link is through the second law of thermodynamics. This law states that the entropy of any isolated system always increases. It's like a cosmic rule that nature follows. Imagine a building collapsing. It moves from a state of order, a well-structured building, to a state of disorder, a pile of rubble. This is an excellent, real-world example of entropy increasing in a system. But why does entropy always increase? Why can't it decrease? The answer lies in probability. There are far more ways for a system to be disordered than ordered. So, statistically speaking, a system will naturally gravitate towards a state of higher disorder or higher entropy. Entropy is not just about disorder though, it also has a direct relation to the amount of energy in a system that's available to do work. When entropy increases, the amount of energy that can be used to do work decreases. This concept is often used in engineering and other fields to understand and optimize energy use. The second law of thermodynamics and its link to entropy also provide a fascinating explanation for the arrow of time. Because entropy always increases, we can determine the direction of time. If we see a video of a building collapsing, we instinctively know it's playing forward because the building is moving from a state of order to disorder, not the other way around. So, entropy is the reason why time only moves forward and not backward. Fascinating, isn't it? Entropy isn't just limited to physical systems, it can be applied to information theory as well. Now that's a statement to stir curiosity, isn't it? But how does a concept from thermodynamics find its way into the realm of information? Well, in information theory, entropy measures the uncertainty or randomness of information. Just like in thermodynamics, where entropy measures the degree of disorder or randomness of particles, in information theory, it quantifies the uncertainty associated with random variables. So, how does this work? Let's say we have a set of messages. Each message has a probability of being chosen. The entropy in this case would be the sum of the probability of each message times the log of 1 over the probability. The result is a measure of the average amount of surprise or information that you get when you learn the outcome of the variable. But why is this important? Well, understanding entropy in information theory has many practical applications. It can help in data compression and encryption, for example. In data compression, entropy is used to determine the minimum number of bits needed to encode a set of data. The higher the entropy, the more bits are needed to store the data. In encryption, entropy plays a crucial role in generating keys that are hard to predict. A key with high entropy is more secure because it is less predictable and harder for an attacker to guess. In essence, entropy is a measure of unpredictability. Whether we're talking about the disorder of particles in a physical system or the randomness of information, entropy is there, quantifying the uncertainty and providing a framework for understanding and managing it. So next time you zip a file to make it smaller, or when you use a password to secure your accounts, remember that entropy is at work. It's not just a concept in physics but a universal principle that governs our world. So entropy is not just a concept in physics but a universal principle that governs our world. To wrap up, let's revisit the key points about entropy. In its most basic form, entropy is a concept in physics that measures the level of disorder or randomness in a system. It's like the ultimate rule of the universe that insists, hey, things like to get messy. Now don't confuse entropy with chaos. Entropy is not about chaos, but about the number of ways we can arrange the particles in a system. Think about a deck of cards. If you shuffle them, there are countless ways those cards can be arranged. That's entropy in action. In the world of thermodynamics, entropy is a superstar. It's the guiding principle behind the second law of thermodynamics, which states that in an isolated system, entropy can only increase. This law defines the direction of time, from past to future, and is the reason why your coffee cools down to room temperature or why ice melts into water. Entropy is not just confined to physics and thermodynamics, it plays a vital role in information theory too. It helps us understand the amount of data that can be stored in a given space, or how much information can be transmitted over a network. The more entropy, the more information can be packed in. But entropy isn't just something you'll find in science textbooks, it's all around us. Every time you see a pile of leaves scattered by the wind, a room getting messier day by day, or even a crowd of people exiting a stadium, that's entropy. It's the universe's way of saying that there are more ways to be disorderly than orderly. So entropy is not just a scientific concept, it's a fundamental aspect of our universe. It's about possibilities, the freedom of particles, and the inevitable direction of time. It governs everything from the cooling of your coffee to the complexity of the internet. Next time you see a melting ice cube or a messy room, remember, it's all about entropy.